Welcome back to engineering. Today we're going to talk about parallel circuits. So what you'll see up on your screen is from your work package, and we're basically talking about parallel circuits and Kirchhoff's current law. So the big idea here with Kirchhoff's current law basically just says that the sum of the currents in all of the branches defined by the nodes is equal to the total current through the circuit. So let's take a look at what that means for a second. So what we're talking about here is we've got a voltage source or supply, and we don't know what the setting of that is, V sub t, a battery or some DC power supply, with a current total coming out of it. And that current is split over the branch I1, I2, and I3 through resistor 1, resistor 2, and resistor 3. Now, this goes on for as many nodes as there are in the parallel circuit. And when I say a node, essentially I mean an element that's wired in parallel. So as an example, resistor 1 is in parallel with the battery. It sees the full voltage of the battery. So does resistor 2. So does resistor 3. So that's my next statement here, is the voltage total, or the voltage of the source, is equal to the voltage across each element in the nodes. So VT equals V sub 1, which also equals V sub 2, which also equals V sub 3. This last idea is the resistance total is proportional or equal to 1 over the sum 1 over R1 plus 1 over R2 plus 1 over R3. That is derived from the formula above, which says the inverse of the total resistance is equal to the sum of the inverses of the individual branches. So if you actually did the algebra, you'd see that to get R total by itself in the numerator, this is the equation that you'd end up with. Now the last big idea that's not commonly taught here is that the total resistance of the parallel circuit, or the equivalent resistance of all three of these in parallel, is always going to be less than the smallest resistor in the circuit. So let's take a look at a circuit. So let's look at this circuit. What we have for supply voltage out of the circuit itself is this 10 volt supply. So I've got a 10 volt supply which is supplying the voltage across resistor 1 and resistor 2. So I've got two nodes to this circuit. Now there's a couple different ways we can find the equivalent resistance. First I'm going to use the formula. So remember that formula just says that the resistance total, or RT, is equal to 1 over the sum 1 over R1 plus 1 over R2. Now, it looks worse than it is, the math, if you do this in your calculator. I'll just caution you to use your order of operations. So in this instance, my resistance total is going to equal 1 over 1,000 ohms. That's 1 kilo ohm, plus 1 over 10 ohms. If I do all of my calculations on that, I'll get my total resistance is going to be equal to 1 divided by 1,000 plus 1 divided by 10. And I get 9.9 ohms. Now, for significant digits here, I can carry that out to one digit past what my data input was, so that'll be 9.9 ohms. Now, I can check that pretty easily also. So let me record that, 9.9 ohms. I can check that pretty easily also through another method. So this is my RT. And what that means is I could draw this as an equivalent circuit, and it would be represented by this symbology here, 9.9 ohms and 10 volts. Now from this, I can use Ohm's law, and I can basically say that Ohm's law, remember, our basic Ohm's law is V equals I times R. I can also solve for current. I equals V divided by R. And I can also solve for resistance. R equals V divided by I. We're going to go ahead and use this in blue. We're going to use this solution right here. We're going to solve for the total current. And this would be IT. So let's go through and do that. IT now is going to equal to my total voltage, which is 10 volts, divided by my total resistance, which was 9.9 ohms. Pull up my handy dandy calculator, and I get 10 divided by 9.9. I get 1.01 amps. Now, I can also solve this by the individual branches. So as you recall, in the individual branches, and my other, one of my other laws here was that my branch voltage here is 10 volts. And it's 10 volts in the second branch. So I can also find the individual currents, and I'm going to call this I1 and I2, a different way to solve this same problem. And over here, I could say that I1 is going to be equal to 10 volts, again using Ohm's law, divided by 1,000 ohms. And I2 is going to be equal to that same 10 volts divided by 10 ohms. Pretty quickly, you can see that this ends up being 1 amp, and this ends up being 1 milliamp, or 0.001 amps. Sorry, 0.01 amps. It's 10 milliamps. Sorry about that. 10 milliamps. 0.01 amps. So let me erase this off here a little bit. It's 0.01 amps. Now, Kirchhoff's current law says that the current flowing down through here, I2, plus the current at I1, is I total here. So this is my I total equals to I1 plus I2. So now what you can see, that again equals 1.01 amperes when I add those up. So I did this two different ways. I found IT, 1.01 amps, by finding the equivalent resistance and the total voltage. I also found IT by looking at the individual branches. Now, if you can do those two methods, you can solve all of these parallel equations. Thanks for watching.